maybe I'll say a bit more about general things afterwards. We know that there exists which is an initial representation. Initial algebraic gate. See that? And what we want to claim now that this space, this variety, is zero-dimensional. So the dimension of the stabilizer is the same as the dimension of the space to begin with. So later on I will claim that H is G. This is essentially what I'm supposed to prove. First of all, I will show that the dimensions 0 and or maybe proof model the claim follows from we've seen. This was a lemma in the course of maybe I'll just erase that. And we've seen before that we've seen that if x squared is ergodic, then x has no countable or finite non-trivial factor. So dg equal dh, then g mod h is finite, of course. It's a zero-dimensional variety, and x goes to g mod h is a point. Must be a point, single one. Which is, of course, fixed by S. And of course, the stabilizer of the point is everything. So the stabilizer of that point is everything. So it's all about this dimension. And now I want to say the following. Now I want to claim to consider for each n the map from x to n to g mod h to n. And once I consider it as s to the n to g to the n, as if brought the n from s to the n to g to the n.
This is the proof the claim?
Sorry?
This is the
yeah, proof the claim. I have s to the n acting here, and g to the n acting here, and this is a covariant. This is a covariant s to the n map. Then, as then restrict to the diagonal inside S to the n, and recall that x to the n is algebraic, is S algebraic. So to do both things. So let's start with one. One tells me. Okay, so remember that this is a space with a measure class. And this measure class I can push here. I can look at the measure class that is obtained here. And measures, for whatever measure in this class, I can talk about supports of measures. This is the minimal closed set that the complement is a trivial measure. And obviously I can also talk about the Zariski support of the measure. The minimal such, which is also Zariski closed. Or if you wish, just the Zariski closure of the support that you're used to speak about. So consider the Z support of the image in G1 dash 3. This is an algebraic set inside this variety. The dimension of this variety is n times the difference between these two dimensions. This is a variety of some dimension, and I'm talking about some algebraic subset of it. And the claim is, obviously, the measure here is, the measure class here is invariant by S. So the measure class here is invariant by the image of S, and also the support. This is an S to the n, or n S to the n, if you want, or of S to the n invariant algebraic subset. But if the stabilizer of an algebraic subset is always Zariski closed, is an algebraic subgroup. So this is the same as rho S equals Z to the n. This is just G to the n. And everything. So far, by the invariant, the S to the n invariance, I see that the image here is essentially dense. Two, but the ergodicity of the diagonal of the diagonal S, the support, sorry, the measure, the push measure, must be supported on a unique orbit. Unique, say, diag G orbit. Right? Consider this variety as a G variety. G is a diagonal. Whenever I have a map from an ergodic space, consider this as an S space, ergodic S space, and I'm pushing it to a variety, an algebraic representation. And this is yet another lemma that we've seen. Whenever I have a representation of an ergodic space, the support must be, the image must be supported on a unique G orbit. This unique G orbit somehow is the image of the initial object associated to the representation of x to the n. I don't care about it. this one. I raised the fact that we are dealing with G mod H, which is the algebraic gate of X. We are dealing with the initial representation, which we wanted to show it is a point. But we already state this claim and we saw this enough. So what we're arguing is to show that dg equals dmh, or dimension of G mod H is 0. But now, again, we push the measure here. We hit one G orbit in here, but this G orbit, now, G mod H to the n has a dense G orbit in it. The image is put on one orbit and it must be dense by one. Such an orbit must be open. Remember, the closure of an orbit is always, also, every orbit is locally closed. It's closed in its orbit. Orbits are locally closed. So it is open in its closure, which is everything. So the dimension of that orbit must be the dimension of G mod H. To the n. N times. And of course it is less than the dimension of G. And this is for all n. Okay? Happy? So then let me now state a very neat theorem. Here is sometimes this one is called Bader theorem. Say G theta equal S, sorry. G. Here, for stating this theorem, S and G will be the same. And the rho will be just the identity map. So, and now X, try to make X to be V itself with a measure. Every measure, G invariant, for an algebraic G variety, V, I can look at G invariant measure on this V. Think about it as my X. Well, actually, take an ergodic one. Of course, the probability measures, the invariant probability measures, are just convex combination of ergodic ones. Let's try to understand what an ergodic probability measure, invariant probability measure on V might be. Well, take V comma this probability measure measure to be my x. Take S again to be G, and rho to be the identity map. And the map from X to V will be the identity map as well. And we see that this probability measure, the ergodic probability measure that we're considering now, must be supported on a fixed point. And this is for every ergodic measure, and for every measure altogether, whatsoever. Okay. So this is the same as probability measures only. I mean, always we have this containment, right? But this is the same. So why does it call Borel density theorem? So this is an extension of, this is what Borel proved to begin with. If gamma inside G is a lattice in a simple group, then there is a closure. Why? Consider, well, we have a measure here, and push it to this thing. Like this representation of X. And oh, maybe I didn't say it. I was using the fact that this thing comes from 3 by what we've done before. And the image in that field must be a fixed point. So this V actually must be 1 point. Okay, any question? So now, oh, and by the way, so this is maybe one remark on this. We've seen here that for whatever algebraic representation of S, if I do have this with mixing, the initial point in the category of representation of X will be a point, a fixed point. And this is actually independent of G itself. I could consider here, mark maybe, we may consider a more general category. Of reps of S on X. So here's a representation will be a pair. I'll get a color. The white is the given data, and so this is indents. Group representation, and this will be an action. So I can represent both. I can represent the action of the ergodic theoretical groupoid here in that algebraic theoretical groupoid. Previously, we fixed that part as well, and vary only this. In principle, I can consider this, and then morphisms will be, no, not just plain. There is a reason why I'm presenting it. We will not do it, but just if we would, That's what morphisms will be. I'll have a morphism will be a map to V, a map to U. I mean, I guess that will be the morphism. This is the given two representation. But here I will have GU acting on V, GV, GV acting on V, GU acting on U, and of course I will have S mapped here, mapped there, and now I want to say that then naturally probably you're guessing that part of the data that I will define morphism with will be with a homomorphism, algebraic homomorphism between these groups. This I don't want to do because somehow maybe this is a point, and this is okay. If you think about it, what you get is that you want here something like that, and the representation here, so such that everything agrees. Okay, so this is a possible nice category to consider. Somehow, again, it reflects better not the representation theory of X relative to the given representation of S to G, but altogether. I prefer not to consider this because for this category is too big and I will not have an initial object. But this theorem actually applies for this category as well. This has nothing to do with G. In fact, for a given G, if you follow this argument, I need to assume ergodicity only up to some power for a given G to get the result. But if I have ergodicity for all powers, then I have it for all G simultaneously. Okay. So now I want to come up for some reason with yet another category for representations. Slightly complicated, but there is a reason that I'm presenting it. So now I will take by actions. So now pick, let X be a vector space. And though with commuting actions of somehow I will break the symmetry. So I will have X, and I will act with two groups on it. So not to emphasize that there is this commutation, I will act with one on the left and one on the right. And one I will call gamma, and one I will call U. I mean, you may think of them in equal footing, but for applications, I mean, I guess there might be hints in the notation. With actions of LCSC groups, gamma and U. Assume, so then the U times gamma action of X is ergodic. In fact, soon I will assume more. But just to make a definition, I want now. So this is a by action. This is the bi-algebraic action. Similarly, I might consider bi-algebraic actions. A bi-algebraic action is, well, G times L acting on something. Again, I will think of this commuting action as if one acts on the left and one on the right. A representation. Okay, maybe I should say some words. Now I can either define a representation as in the first version we had, fix a map from gamma to G and from U to L, and consider the associated representation of X. This is the same, but as taking the group gamma times U acting on X and the algebraic representation of it to G times L, if I'm fixing all the data. I can either not fixing all the data, but this is the same as not fixing G and L here. I'm trying to say, if I will not fix representation from gamma and U to either G and L, not fixing G and L as well, then this is as taking S here to be gamma times U, and G here to be some product. So what I want to do now is a mixed version. A bi-representation of, so fix I'm fixing this, of course. I'm fixing G, and I'm fixing rho from S to G. You see this? This is the fixed data. I will not fix L. So I'll vary L, maybe. So, excuse me. This U, this is gamma. I will not fix the map from U to L, which that's called theta, and I will not fix here. So a representation will be a choice of such things. A representation. L, theta, V as above, and the map from X to V, which is, well, I guess I have here gamma times U, rho times theta, to G times X. So I'm considering bi-actions, and I'm kind of fixing half of the data and letting loose the other. And more physics of representation will be modeled on this, on what I had here. So let me just redo that one. I'll rewrite this. So I'm having G times L here, G maybe LU. Typically I'm calling, I'm thinking of the representation as the representation space, and I will use these as a subscript to know the object correspond to it. PU, PV.
Maybe U is okay. Maybe W? Maybe W?
U is the name of the group. Right. Thanks. And okay, so this acts here. G times LV acts over here. And I'm having the corresponding maps. this rho times W, rho times theta V, and I want the corresponding, I want now to relate this, so I will say that this map is equivariance. So I want this map, of course, to be an algebraic map between these varieties, which is G equivariant, but it also equivariant with respect to the L's. But again, I don't, like, I have to relate them. So I will have one guy, L, which maps to both L's. So by this, L act on W and L act on V. And I would ask this map to be L equivariant. And of course, this should be related and yeah, I guess let me write it here. And I'm having U here, and I'm having this map theta W. This is not the map. This is just saying that this arrow is equivariant with respect to this action. It's not the name of the arrow. I'm having this map here and that map there, and I'm asking as part of data to have some thing relating everything. So this is the complicated diagram that I want to consider as a morphism. This data is a morphism. Between you and me, I think of that guy. Just that guy. Yes.
What are the errors between the x and the g times L whatever?
So I guess I should have. It should. Yeah, I think. Sorry, I should have written. What I had in mind when writing is that thing, and somehow I didn't write it. And here is, I guess well, I like the symmetry, sorry. So this is all times here, or something. Okay, is this clear?
No.
This is important, and let's take some time to absorb. What?
Das ist dann G gevoel.
G כפול?
L.
G כפול L, okay.
So you have this homomorphism from G cross L to this both.
Oh, actually, I want to almost. This is identity times
Identity.
something. FW identity times FV. Again. So if you just ignore this L, are things clear? So if I, of course, if I just ignore the acting groups, then everything is clear.
The question is, you have this map from W to V. I suppose it should be G equivariant.
Yes, it should be G
But
equivariant.
what's the equivariant
Yes,
with respect to the second?
So it should be, okay, if it would have been the same group here and there, I would ask this to be equivariant as well.
Yeah.
Naively, actually, you would ask to have a map from this to that, which commutes everything. But somehow this doesn't, I mean, if you try to think about it, you see that you want this guy and that guy to have a common father. So once they have a common father, the divide group L that is mapped onto this and onto that, then so this is on. Then it does act on W on V, and this is Z-dense homomorphism. It does act on W and V, and I can ask this map to be not only G equivariant but also L equivariant. So this is what I'm asking.
The existence of such a map.
Yes. So just a representation is very similar to, I mean, is this data. It's not so far from what we had before. We add the choice of L and the homomorphism to L, and ask the actual representation between space to be equivariant with respect to it as well. The morphism is again slightly more complicated because somehow I have to, if you want, below this there is the category of just a category of algebraic groups with such a diagram being a homomorphism, a morphism. I mean, when you consider the category of groups or algebraic groups, I can consider object to be groups and morphism to be homomorphism. I can also allow morphism to be such that diagrams, and this makes sense sometimes.
It's just, you mean, like the stupid idea to take the product doesn't work, of course, because that's not equivariant with respect to the projections.
No, it is. Take the product, basically
If
what
we take the product LW,
of the L's.
yes, it's not equivariant with respect to the projection nodes.
Well, I mean, these.
But
Yes,
it seems to me that from all the data that you require, it's almost like
It's
L is the graph of homomorphism from LW
Yes.
to LV.
Yes, yes.
And I wonder, can't you just say it then?
Okay, the truth is that this when it was first written down, this is how we wrote it, and there was a slight mistake in it because somehow you have to inflate. Maybe for some natural example that appear, maybe these okay. The example that I'm having in mind is V is a certain variety, W is a subvariety, maybe an orbit in it, and the action and L is acting on that variety, and but the action on the orbit as a kernel to it. Maybe L acting faithfully on that, but the action on the orbit as a kernel to it, and mistakenly you choose that LW to be L modulo that kernel. It does act here. And then you cannot map this one to that, you have to inflate first. So you should think of this as a graph homomorphism plus the possibility of inflate the action. This is it. Okay, does that make sense?
Yeah.
And probably my time is up,
But in many cases, it's probably good to think of it as a graph.
yes, I guess
So
as a
it's
first
very-
approximation, you should think of it as a graph homomorphisms, and I guess that I will start next time. Is my time up?
Probably.
Yeah. So I'll just tell you what I'm about to do. Next time is our last meeting, and I came to this slightly complicated formally, but it's yet natural in some sense. So I will start by this, and I will explain why, if I take this category plus some extra ergodicity assumption that is reflected here, actually this G here should be L in that story, I will still have an initial object to that category, and then we'll do marvels with that. We'll prove Margulis superrigidity in a quite formal way. And I will explain.